Good. I think we'll get started and people can join in as we're doing introductions. We'd like to begin today by acknowledging the land that the Hive is on is the traditional territory of the Ohlone tribe. So we honor their history, culture, and ongoing contributions to this land and recognize they were guests here. With that, I'd like to hand it over to the manager of the Hive Think Tank, Olivia Yang.
You're on mute, Olivia.
Oh, sorry. I think I'm on mute. So good morning, everyone. Thank you so much for joining us and welcome to the Hive Think Tank webinar series. So my name's Olivia and I'm the operations manager at the Hive in Silicon Valley. We're super excited to have everyone join us and hear from our expert panel speakers from Atom Computing, Quantination, IBM Quantum, Atlantic Quantum, and Qubit Pharmaceuticals. So with that being said, I'll quickly go over some of today's best practices for the webinar and explain what the Hive Think Tank does. And then I'll pass it back over to Ravi, who is the Hive's founder and managing director. So we do love questions. So we love for the audience to use the Q&A button to ask our panelists questions and not the general chat box at the end of at the bottom of your screen, which they'll answer kind of during the end of the presentation, end of the panel discussion, but then also kind of here and there throughout. The session is also being recorded and will be available to view later on our YouTube channel. So the Hive Think Tank is an ecosystem of thought leaders, corporations, and entrepreneurs. We're an event and content platform with a focus on AI, enterprise, security, sustainability, health tech, and so much more. We do host events almost every other week on cutting edge topics in technology and business. So I would highly suggest for our audience to join our meetup group and newsletter to stay up to date on our events. And I'll link the meetup group in the chat below. So we do also have another webinar later on this week. It's on Wednesday evening with our Hive Southeast Asia team, where the panelists will share their experience on innovating and building sustainable business models, while also creating value for their customers and employees. So I'd also like to thank our sponsors, Avanta Ventures and Gamuda, for their support. And for our audience, if you are interested in getting involved with the Hive Think Tank, feel free to reach out to me at olivia@hivedata.com. And then feel free to also follow us on LinkedIn and Twitter. So with that, I'll go ahead and pass it over back to Ravi, our managing director, to talk more about the Hive and introduce our speakers.
Thank you, Olivia. Welcome to everybody. My name is T.M. Ravi. I'm the managing director of the Hive. The Hive is an early stage venture capital fund focused on applications of data and AI across a variety of different horizontal and vertical use cases. We're also very early stage investors. So we help entrepreneurs start companies and participate in early stages of financing. Next slide, please. In addition, next slide, Olivia. In addition to what we do in the US, we also have entities in Brazil, Southeast Asia, based in Malaysia, India, and later this year in Europe. All the different venture entities throughout the world are early stage entities that focus on data and AI. Next slide, please. We have later this week an event that we are co-hosting with the Hive Southeast Asia, and this is an event focused on impact investing. And I hope that you'll be able to join, and this is going to be at 6:30 p.m. Pacific Daylight Time. Next slide, please. By the way, another event that we are planning to host is on April 26th, and it's going to be on generative AI. And so we'll be posting that event on Meetup soon. So I hope you can join. We are excited today to be hosting this event on quantum computing. There's been a lot of excitement in the space. In some cases, a lot of hype also. And so, starting from the fervor of some of the people in the quantum space matches the fervor of the crypto people. And so hence the title here. We would encourage you to ask questions, and so use the Q&A button on the bottom. And so with that, I'd like to introduce the moderator of today's event, Christoph Jurczak. Christoph is the founder and partner of Quantonation, which is exclusively focused on quantum companies. He's got a PhD from École Polytechnique in quantum physics. He's spent time in government service and corporations, and more recently as an investor in this space. But today, if you're going to be tweeting, please use the hashtag Hive Data. And with that, I'll hand it over to Christoph.
Thanks, Ian. Thank you very much. And thank you all for making it this afternoon. Based in London currently. Robert is in Paris. I think our 3 other speakers are in the US. It's really a privilege to be here today, to have you all. I remember a meeting at the Hive, I think in Palo Alto, like 5-6 years ago, but IoT was a great experience. Too bad we can't have it in person, but I think that's a very timely topic. Pretty hot discussions around this topic these days. So I'll try to moderate the panel today and to generate some lively discussions. I have my own views on the topic. Probably people who know me know that I'm a big proponent, a strong believer in short-term applications of quantum computers. I think it's going to be interesting to have this conversation, but I'll try to put my beliefs a little bit in the back and try to generate and convey the excitement that we all feel when we are working in this sector. Just a few words to start about Quantonation, and then we'll have an introduction by each of the speakers today. So, as mentioned earlier, we're a fund dedicated to quantum technologies, not only quantum computing. We're active also in sensing, in communications, and a field that I call deep physics or quantum 1.5, a little bit less quantum, but with the same kind of applications, same kind of companies, maybe a little bit shorter term than the others. And we have made 24 investments so far, plus 2 exits. For our first fund, Quantonation 1, which is a 90 million fund based in Paris and Boston. And we are currently raising a second fund, which is bigger, that we plan to invest from as soon as this spring. We've started in 2018. We've seen, let's say, catch the wave, I tend to say, quantum technologies. We've seen some very early stage companies turning into scale-ups as of today. So lots of experiences to share about that as well. But maybe now we can switch and have each of our speakers introduce themselves and tell us a little bit about their company, what they're working on at the moment, and what keeps them excited. Aparna, do you want to start?
Yeah.
No. Yeah, Aparna, yes.
I don't have slides. So good morning, good afternoon, everyone. My name is Aparna Prabhakar. I am Vice President at IBM, and I'm responsible for the quantum ecosystem at IBM. In this role, I own the development, growth, and delivery of the market for quantum. Now, when you speak about IBM, I always like to start with what we are doing at IBM, our mission statement. And our mission statement is very simple. We are working to bring useful quantum computing to the world. And that at the heart of it is enabled by our development roadmap. So if you Google us and Google IBM Quantum Development Roadmap, you will see a roadmap which goes all the way to 2026. And today we have 127 qubit machines, which are available on premium plan for our network. And in a week, we will have 433 qubit machines, which will be available to our ecosystem. We've developed both middleware and are developing the software alongside our partners to enable quantum computing. At the highest level, you can access IBM Quantum through 3 ways. You can join our open plan, which is 5 to 16 qubit machines. You can access it through consumption-based model, which is about 27 qubit machines, and then finally access the whole set of systems with premium plan, which is 27 plus qubit machines. And we have over 26 machines today currently available to our ecosystem. I have about 220 partners in my ecosystem, which span startups all the way to national hubs. And if you looked at the news, last week was very momentous for us. We actually inaugurated our Cleveland Clinic relationship, where we put our first 127 qubit machines on site, and also announced our engagement with Spanish government with Ikerbasque quantum computing. I'll move it over to the next speaker. I believe it's Rob.
Hi, I'm Rob Hayes. I'm CEO of Atom Computing. My background, prior to joining Atom Computing, I was the Chief Strategy Officer at Lenovo for their Infrastructure Solutions Group, which was x86 server business they'd acquired from IBM a few years ago, and storage. Prior to that, I was at Intel for 21 years. I ran the Xeon processor product line there and managed the data center silicon portfolio. So my background is computer engineering. I got engaged with Atom Computing in 2020 as a board member and joined as CEO in 2021. What Atom Computing is, we're a quantum computing hardware company. So we're building quantum computers out of optically trapped neutral atoms. So we've got these atomic arrays of qubits that are basically trapped in a vacuum chamber with lasers, and we can manipulate their quantum states using different pulses of light. The technology has the opportunity to scale more quickly than some of the initial modalities. And so we have a 100 qubit prototype system that we've been working on for a couple of years now. And we're currently building production systems that prove that we can scale up that technology. And so we'll have product announcements around availability in the coming months on those systems. And we support, common software programming languages like Qiskit from IBM and OpenQASM, so that people can port their algorithms, from another platform to our platform and vice versa. Pretty easily. So we're trying to be very partner friendly and work with various application providers and end users to program these systems, using a gate-based model and circuits. So that's us, and I'll turn it over to the next person.
Bharat, yeah, okay, we're good.
Hi, I'm Bharat Kannan. I'm the CEO, co-founder of Atlantic Quantum. A little bit about myself. I'm originally from New Jersey, did my bachelor's at Rutgers in physics, then moved to MIT for the last 6 years, did my PhD in the group of Will Oliver, and most recently, myself and several other members from MIT, the MIT team, started Atlantic Quantum. So we are a relatively new startup in the quantum hardware space, where we are working to build fault-tolerant quantum computers based off of superconducting qubits. So a little bit about Atlantic Quantum. Our mission is really emphasizing fault tolerance. Maybe Christoph mentioned earlier about near-term applications. I wouldn't say the opposite of that, but our central mission is, what is the quickest path to fault tolerance? Because we see the maximum value of quantum computing occurring when we get error correction running. And so we're very focused on, thinking about what are the fundamental bottlenecks and brick walls that, in particular, superconducting qubits will run into when trying to achieve fault tolerance. And specifically thinking about, how are we going to engineer the systems, the sizes of the systems that are going to be required, and the performance in terms of error rates in order to keep the system sizes as low as possible. How are we going to engineer that and get to that point of error correction? And so we are, pretty much singularly focused on making sure that our hardware, both in the near term and the long term, are bounded by the constraints of a fault-tolerant quantum computer. Yeah.
And finishing with Robert.
Hi, everyone. Thanks a lot for inviting me. So I'm Robert Marino. I'm the CEO of Qubit Pharmaceuticals. A little bit about my background. I'm a chemist by training, then did a PhD about 15 years ago on quantum memories in solid states, rare earth-doped single crystals. Then moved for the next 15 years in technology transfer and early stage incorporation of startups. So I created an accelerator in Paris and then worked with Christophe on helping young companies spin off from academic labs. There were some notable alumni such as Pascal, Alice and Bob, etc. So quantum became a strong stream. And that's how we met with the academic founders of Qubit Pharmaceuticals. And how I decided to join the company and help develop the company. So Qubit Pharma is a drug discovery company using a proprietary platform called Atlas. It was launched during the second quarter 2021. We are now about 50 people in France and in the US. And what makes us unique is that we try to leverage both classic computing and hybrid HPC QC platforms. That means we don't oppose classic and quantum computing. We don't say that quantum computing does solve all the drug discovery problem, but rather try to find the best way to use each type of platform in order to solve hard computational problems. And while we are waiting for hardware to come, we have developed our own simulator using GPUs to be able to emulate about 40 qubits on a quite average on a daily basis, which helps us in our drug discovery programs.
Okay, thank you very much.
Yeah, no, that was it. So that's basically a summary of what we do.
Okay, thank you very much. So yeah, as you've seen in the presentation to the webinar, we have we can go into some pretty technical discussions about some of the qubits that the companies here, so IBM, Atom Computing, Atlantic are developing, which are vastly different, and I think we'll go into it. But first, maybe I wanted to ask a question, maybe starting with Robert, and have everybody also give me their view on that. It's about why at all we should need a quantum computer, actually. Is there really a need for that? I mean, why develop this technology? I mean, probably many of you have seen NVIDIA's CEO speech last week at GTC. Pretty impressive, as usual. GPUs are improving. They're dealing with more and more applications satisfying the user's need. Why at all are we looking at quantum computers? Is it not just quote unquote physicist's dream to get to build a computer out of qubits? Is there really a need for that? And maybe I will start with Robert, since you said you were working both on quantum processors and classical processors. How do you assess the need actually? Why would you like to have a quantum computer at all in your workflow?
Thanks for the question, Christophe. So actually, we are not developers of quantum computers, so we are users and clients. We wish to buy a quantum computing time in order to solve complex problems. What we sell at Qubit Pharmaceuticals are drug candidates. It's IP that covers small molecules. What our clients look at is just how good the drugs are, not how we met them and how we found them. So whether it's with classical or quantum means, it's not a problem to them. What they want is efficient drugs. Now, the thing is, finding drug candidates using computational methods is expensive, can take a lot of time. And we have been working for quite some time, and the academic founders for about 30 years, at optimizing computational workflows. And by doing so, they moved from one hardware platform to the next. So it started with CPUs, then parallel computing on CPUs, then single GPU, then parallel computing on GPUs. And what we see now is a new hardware platform, quantum computing. So what do we expect from quantum computers? There are three ways that we think that using a hybrid HPC QC could improve drug discovery. The first one is eventually we solve math problems. So some of them are not fully solved on classic means. That means we still have some errors on the computation that can impact the speed of discovery of novel compounds. So that's the first thing that we hope with QC. It's an improvement in accuracy. The second one is faster convergence of our computation. So today we use a lot of GPUs. Eventually we end up with a solution But intrinsically, since QPUs are massively parallel, we could find the same solution faster. That saves us compute time, and in the end, that's cash, so we're more efficient. Last one, imagine we were about to find the same solution than with classic computing. What we could expect, and with the same time, same quality, we could also sometimes expect on some algorithms that QPU will consume less electrical power than GPUs, which means saving money also and being faster at finding a solution, especially doing quantum computing. So these are the three ways that we explore. But so far we don't have the answer. We think it's worth exploring it, looking at R&D, trying to find problems that would benefit this hybrid infrastructure. We are convinced that eventually we'll find solutions, but unfortunately I cannot give you the answer yet.
Aparna, do you have a point of view on this, since you have a fairly large ecosystem as well? The largest ecosystem in the world, probably, with IBM, both with software developers, users, you have the hardware as well. How do you approach the needs, actually, even before we talk about the technology? And since you're also providing HPC, large supercomputers to your customers, how does the quantum and the classical part of the business at IBM actually converge together towards the user's needs?
So the way I think about quantum is put it in a paradigm, right? So it's quantum, GPU, and QPU in some ways. And when you'd started with comparison on quantum and GPUs, and I think they serve actually different purposes. If you think about GPUs, they are specialized processors that are really optimized for performing parallel computations with a large amount of data. And they're based on classical computing principles, but they're not suitable to solve certain type of problems that are inherently quantum in nature, like simulating quantum systems, optimizing really complex functions, and searching things like unsorted database. Quantum, on the other hand, is designed to harness the unique properties of quantum mechanics, such as superposition, entanglement, where it forms a complex mix of zeros and ones. So the complexity, you can process a lot more complex data. Now, that means there is a reason why quantum computers make sense, and it's not going to replace classical. It is going to be in parallel with classical. And the way we think about it at IBM is we are actually creating orchestration, and we're working with our partners to think about how classical and quantum will get orchestrated. So when you're a developer and you're sitting with your workflows, the ideal scenario would be the developer doesn't need to know what is classical, what is quantum eventually, right? They would be able to put in their workflows. The classical bits get processed with GPUs or classical HPC compute, and the quantum pieces get processed with quantum computer. And eventually, both of these get integrated together to deploy as a workflow. And these use cases will be relevant in all the areas and industries we are speaking about. So to me, the question whether quantum should be its own field or not is almost a given because of the value unlock it brings differently than classical and new set of use cases which it will bring forth.
Okay, thank you. And maybe switching now to Rob and Bharat, I will ask you maybe each of you to say a few words about the technology that you're developing specifically in your companies. Like what kind of qubits are you working on? At what level of scale are you currently? So how many qubits essentially? I guess maybe some other parameters you want to highlight. And from there, how you are addressing the customer's needs, since you are startups, less funded, obviously, than IBM, maybe with a smaller ecosystem currently, and maybe you try to build a bigger one with time. So it's a good question. After you give us some details about the technologies you're developing, is how do you connect with users in the end and make sure that the technologies you're developing are useful for somebody?
Sure, I
Rob?
guess I'll go first. So just maybe one quick kind of comment on the last question too, which is, you just think about engineers designing anything across any sector today. Over the last couple decades, they've really moved from what would have been like physical design to digital design, right? Cars, planes, motors, everything is designed in the digital realm today because it's so much faster and cheaper, right? To design things and like crash, virtual cars that are simulated or things like that versus real cars, right? And with quantum systems now we have the opportunity to simulate and model, chemical reactions, energy, physical, subatomic physical systems that just really aren't practical to do on a classical system. And so being able to supplement a classical system with a quantum system to go simulate, the next level of these systems so that designers can design whatever it is, products or networks or whatever they're trying to design in a much more efficient manner, I think is like really exciting. And in order to do that, they're going to need a lot of qubits, right? Because you need a lot of physical qubits in order to yield a fault tolerant system. The erasure coding, or not erasure coding, the error correction coding and things like that go across these physical systems are going to, yield a relatively small amount of fault tolerant qubits from a relatively large amount of physical qubits. And so the important thing, I think, is to look at what is the scalability of a technology that you're developing. How fast can you scale it up? And then how can you layer on error correction to yield fault tolerant computing? And so that's kind of what is guiding our roadmap at Atom Computing. We're building atomic arrays of qubits out of neutral atoms. We basically take alkaline earth elements, strontium today, and we trap it using what's called optical tweezers in a vacuum chamber. We're able to manipulate the quantum states. We use a nuclear spin qubit. And we use Rydberg states for entanglement to run 2 qubit gates. And so we're able to build these really kind of high quality qubits that have long coherence times because the nuclear spin is so well protected from outside perturbation inside of our qubits. And then we just scale up by creating more spots of light, more optical tweezers that can capture more and more atoms in an array. And that's how we scale, is just more spots of light in 2-dimensional arrays today, and then eventually 3-dimensional arrays of atoms that are floating in free space. We don't have to wire up each qubit, everything's controlled wirelessly. So that allows us to have many qubits in a very, very small space. We basically pack our qubits in about 3 to 4 microns apart from each other. So if you do the math, you could fit 1 million qubits in an array that's less than 1/10 of a millimeter cubed volume, so very small. And the tricky part is basically how do you control the light, the individual kind of spots of light, so you have very precise control over the amplitude, the phase, the frequency of that light, so you have very precise control over those qubits and get very high fidelities. So that's kind of the magic behind what we're doing is how do you take a few laser beams that are on the order of a watt or a few watts each, and then break up that light into these individual controlled beams so that you can control the nuclear spin and the Rydberg states of these atoms.
Thank you, Bharat. A few words, a little bit to give us some perspective on your groundbreaking technology.
Yeah, so we use a very different hardware approach to what Rob just spoke with atoms. We're working with superconducting qubits, similar in fact to what IBM's doing, but a very different type of qubit. So, the current workhorse in the superconducting community for the last, say, decade has been the so-called Transmon qubit. And the Transmon, it's a great qubit. It's basically the simplest superconducting circuit that one can make in order to build a qubit, and its performance has really improved quite a lot since when it was first thought up in 2007. So that's great, but in our opinion, as great as the Transmon is, it has certain bottlenecks associated with it. And the 2 key bottlenecks that we see, and this is not a secret, everyone knows this, is A, error rates, and B, how are you going to scale this up? Right, because like Rob said, a lot of the challenges that we're going to face in getting to fault tolerance is indeed in scaling the number of qubits while maintaining a high enough level of performance. And right now, nobody really has either of those. So we really are looking for a solution that solves not one or the other, but rather both simultaneously. More often than not, you see, if I'm going to try and improve my error rate, that is at the cost of, it increases the complexity of the system, and therefore scaling becomes a challenge. Or I'm going to try and reduce the complexity of my system to control it, but that's at the cost of error rate. So the question is, what is something that you can do that solves both of these problems simultaneously? And we see Fluxonium, which is a different type of superconducting circuit. It is essentially a Transmon qubit, but now you add an additional component, a large inductor to the circuit. So you take a little bit away in terms of the simplicity of the circuit, but you actually get quite a lot back. So by adding this inductor, this effectively lowers the frequency of your qubit by more than an order of magnitude, around 50x. So Transmons typically operate around 5 gigahertz. Fluxonium, it has a wide range, but for us on the order of 100 megahertz. And by doing this, you're able to improve the error rates because the lifetime of Fluxonium is significantly longer, even given that it really hasn't been that much development or as much time spent on Fluxonium as there has on Transmons, right? So, our first Fluxoniums at MIT, for example, were able to break the millisecond coherence barrier relatively easily, which is a challenge for Transmons. But, coherence isn't everything. You actually need to be able to, operate these qubits at a high enough gate fidelity in order to be well beyond the thresholds required for your specific error correcting code, right? So for our case, superconducting qubits is typically surface code. And so the nice thing about Fluxonium as well is because it's at a lower frequency, not only do you get this improved coherence, but it is much simpler to control something that's at 100 megahertz than at 5 gigahertz, right? This is just simple electrical engineering 101. And as a result, we're able to improve the scalability of how we control these qubits compared to Transmons, in addition to the improved lifetimes and therefore lower error rates in our gate fidelities.
And at this stage, how many qubits do you have?
Yeah, so at MIT, we've done up to 16 qubits. So we're currently, it's only been a year since the company started, so we're transitioning that technology over to Atlantic. But yeah, so up to 16 we've done at MIT.
Yep.
And kind of one point to that. Sorry, one more point to add to that question. I think qubit number it's great, and obviously we all need to increase our qubit number. That is a very important factor, but that is not everything, right? When you look at error correction, the number of qubits you need to actually enter fault tolerance scales, very strongly with your error rate. And so an order of magnitude decrease in the error rates can also reduce the number of qubits you need by quite a lot. So just looking at, qubit number to qubit number is typically not the best metric, but yeah, just wanted to put that out there.
Yeah, we'll come back to that. I think neither of you did really answer my question, but I mean, we'll come back to it about how you address customers' needs, actually. But I'd like to take a question from the audience, and I think it's a good one, and that's going to get us into a debate, I'm pretty sure. So the question is, from a computational point of view, is there a known problem where quantum computing algorithms are superior to classical? And there, yeah, any of you who would like to give his perspective, his feedback would be good, knowing that there is a little bit of a debate these days about one very famous algorithm called Grover's algorithm. And I think Rob had gone into some discussions on the topic. So maybe we can start with you and tell us a little bit what you think about, is there any quantum algorithm that could bring an advantage with respect to classical? What's going on with these discussions? Why are we still arguing in a way about the potential or the potential impact or performance or the speed up that a given algorithm could give or bring to end users? Yep. Anybody? Oh, Aparna, you want to comment on this?
For Rob to talk about it. I'm not going to specifically, I actually want to comment about Fluxonium, but we can come back to that a little bit later.
Yeah.
And when you think about, first, today I have about 20 plus enterprises who are working directly with IBM, and then I have about 55 enterprises who are working with our members. And what they are really doing is exploring use cases. So none of the use cases are really in production today. But if we were to look at where there would be quantum advantage, it will likely be in problems that simulate quantum mechanics like chemistry, material science, physics, or problems that deal with structures that is hard for classical computer, machine learning, etc. So when we are working with these enterprises, we are basically breaking it down into 3 big categories, and we are exploring those use cases in those 3 buckets. We have partners who are working and looking at spaces like corrosion problems. They are looking at how do you break it down, what are the proof of concepts in that, which would be relevant. In addition, we have folks in finance who are actually looking at some of the financial problems like portfolio optimization. How does that occur with quantum? But it is very much at the exploration level, and they are exploring these 3 areas. First is simulations, which is quantum for quantum, which mimics the inherent quantum mechanical behavior. People are studying high temperature conductivity, etc. And then the second one is areas like quantum machine learning, which is being done by most of the finance ones. And the last one, where we don't believe as yet, but we are still exploring that there is any exponential speed up, is in the optimization area. So those are the 3 big buckets of use cases which are being explored by the industry that is working with us.
Yeah, I guess I'll add. So, I think optimization does seem to be the one that I see almost the most excitement about. But like Aparna said, I think it's maybe a little bit further out as to exactly what is the algorithm or the use case that people are going to find quantum advantage on. But when I talk to customers and users out there, it does seem to be that optimization problems is very high on the list of sort of what people are looking at. And that includes like portfolio optimization, which you did mention, or, risk modeling and things like that. But another kind of one we see is complex networks. And maybe this relates to the structures you were talking about, but you have a network. It could be a distribution network. It could be a transportation network. It could be it could be a telecommunications network, but where you have many nodes and many connections and many paths, being able to figure out how to route whatever it is you're routing through that network in the most efficient way when you have maybe multi-paths and many nodes is a very complex problem to go solve. And you can solve problems like that on a classical computer, of course, but at some point the network either gets too complex, the paths get too many in parallel and things like that a quantum computer has the opportunity to come in and find a more efficient solution set for that kind of an optimization problem. The other one I think we see a lot of, it's probably in Robert's area, but VQE, variational quantum eigensolvers to do chemistry simulations and things like that seem like a promising one for the NISC-era systems, where there's a lot of interest in seeing if we can model out different molecules and trying to figure out how big of a system do you actually need to perform a useful kind of simulation or calculation using that kind of an algorithm. But we see a lot of interest in that right now as well.
Yeah. Switching to Robert, actually, I think that's a transition I wanted to make. So Robert, what kind of applications are you interested for quantum computing? I'll put in the chat. I think there's a paper your company published, put on the archive a couple of months ago on chemistry. It's often said that chemistry is a prime target for quantum computers. That's where things should happen, or finance is often cited as well. So how do you approach that? What are you focusing on, and where do you hope to see an exponential or quadratic or speed up of any kind, let's say, or something else?
Yeah,
not to speed up.
One thing that is important every time we look at what will be the use of quantum computer, and you touched the point at the beginning of your talk, Christophe, is the benchmark. What are we comparing the algorithm with? And for us, the benchmark will always be computation on GPUs. And actually, there has been a lot done on optimizing even quantum problem on classical infrastructure such as GPUs, and they perform very well. The way we approach, because in our DNA, we really code down to the hardware. We try to understand each type of hardware, whether the provider. We don't approach a problem from a large standpoint, such as can we improve identification of hits? These are the first molecule that you want, but it's rather in the entire workflow, what are the computations that are costly, inefficient, too long, or inaccurate that have an impact in the discovery. So VQE, as Rob mentioned, that's quantum chemistry computation. That's something that we explore. Of course, we hope to see an advantage using quantum computer, and what we try to understand is how many qubits do we need to have an advantage. But very often, what we are going to explore is sampling optimization problems that we face all along the drug discovery problem. So really stepping down from what's the job to what are the technical mathematical problem that we do that are small enough to be able to run on a computer that we'll have access to in the next 5 years. I think as a startup, it's fine to think about problems that will occur that can be solved in 20 years of time, but that's not a business for me. I need to show results on a short-term point of view. So small enough that are valuable. That means that they have an impact in my workflow. And the last one is valuable and repeatedly performed on within my workflow. So that's the way we try to identify the problems. And in the end, it's pure math problem. Can we optimize that equation? Can we optimize that thing? And not as much as we often hear the folding problem or whatever, because these are already very large problems that will require thousands of qubits, or if not hundreds of thousands, and we are not there yet.
Yeah. Okay, so as far as I know, there's not one single quantum algorithm in production currently. So nobody uses a quantum computer in a commercial workflow. Am I right there, or Aparna? How do you see that? I mean, are we still in prototyping or early stage? And when do you expect? That's a question I didn't want really to express like that, but still I have to ask: when do you expect somebody at first to start using a quantum computer in production, whether it's your computer at IBM, Bharat's, Rob's, other technologies over the next couple of years?
So let me start with saying that it's right that there are no use cases which are in production right now. However, I do want to say that you need to think about when you want to take the conversation away from production, because there are many unknowns from there, and start talking about when does value unlock actually start to happen for these clients, where they can do some things which are doable and get better than classical, or be able to do things which are not possible by classical. That is what we are calling quantum advantage, right? And I think about quantum advantage as there are going to be areas of quantum advantage which will start emerging over this year, next year, proof points. And then eventually, as we grow more mature, there'll be more areas which will get unlocked. Now, just note that classical is moving as well, or developing as well alongside. So the quantum advantage is a shifting target in some ways, right? And then I also want to handle one more thing, because this is inherent in your question, is there is this whole idea that there's going to be a magical moment of fault tolerance before that quantum is actually not useful. And we strongly believe that is not true. We believe that there are going to be areas of quantum advantage with error mitigation. And that's the whole thing which we are working towards, is as you're building qubits with speed, with performance, and thinking about the number of qubits, all three parameters, we're also looking at how do you mitigate error for it to be good enough to unlock and to create value. So your question on when will it be ready for production, we think over at least the first use cases which are ready to use will likely be in over next 3 to 5 years, depending on what are the quantum advantaged parameters which we come to get.
Thank you, Aparna. As a neutral observer, I must say I agree with you. So, and now I'm switching to next speaker. So Rob and Bharat, I mean, your company seem to target fault tolerant. So which I mean would be useful maybe to explain a little bit to our audience what's the difference you're making between fault tolerant architectures that you're targeting and NISQ approaches that IBM or other companies also with other technologies, sometimes photonics, neutral atoms, ions, etc., are targeting as well. And how do you bridge the gap from here to then, since you don't seem to believe there is an application landscape that's valuable in the short term.
Maybe
Yeah, I
I'll
didn't say there wasn't. I think we have at least our guy on the long game, which is to get to fault tolerance, and what are all the different technical building blocks and requirements, at a system level in order to finally reach that end state. For us, that'll be multiple generations of systems. We're not just like working on some big fault tolerant system and not have anything in the market until we pop out with it. We'll have NIST systems in the market, probably multiple generations of them before we get to large scale fault tolerant systems. But I think that is the end goal, is to get there. And we will work, just like probably everybody else here, with partners to try to find the applications and algorithms that have quantum advantage in the NIST era in the short term as well. But to kind of answer your question, Christophe, I think, there are multiple things that are required. You need a lot of qubits, you need low error rates, you need error correction codes, you need quality components that have low failure rates, low noise, all those things that go into the system. So it's very much a systems engineering problem, is to look at all the different knobs and make sure that you're delivering, performance and quality, across all those different aspects to eventually reach fault tolerance. But yeah, just to be clear, I think that there are definitely use cases that have the potential to offer, commercial value prior to getting to that long-term state.
So Rob,
Yeah,
I
thank
think
you.
you're saying that fault tolerance is not the magical thing. There are things in between which you can do while we're working on fault tolerance, correct? So I think that is a common view probably we share as well.
Yeah.
So I'm looking at the Q&A and a question as well, so I'm using the opportunity. So any of you want to elaborate a little bit on the difference between fault tolerance and error mitigation? Aparna, you mentioned error mitigation, for example, which is not something that's a different perspective. Can you just say a few words, because there was a question of that, and I think it's just worth explaining what's the difference between full fault tolerance, full error correction maybe, and relatively, minimal error mitigation towards short-term applications. If any one of you want to elaborate a little bit on that, just give simple explanation, that would be great.
Bharat, you want to go there?
Yeah. So before I mean, I'll do this, but I also want to make some comments on previous comments that were made. But essentially, fault tolerance is resiliency by redundancy, right? The idea is that you have faulty individual qubits, and it is like that an individual qubit by itself will never reach the error rate performance of, say, a typical transistor today, right? The transistors basically never fail, but qubits by their nature are fragile objects, and therefore even with the best state-of-the-art coherence and control, etc., they'll likely never get to the same level of performance as a transistor. So how do you actually get to this point where you can perform, millions, billions, trillions of operations without your qubits faulting out? And the way you do that is through this thing called error correction. So essentially, you encode in a single logical qubit, so-called logical qubit. You encode many physical qubits within it, and by operating those physical qubits in synchrony with each other in a specific way, you're able to, even though you have individually faulty components, you're able to make your logical qubit significantly more resilient to errors because of the redundancy that's encoded in it. And so that's essentially what fault tolerance is. Error mitigation is not that, right? So error mitigation is still using the faulty physical qubits that we have today, but really, for example, post-selecting out certain events, such as, some T1 events, or there's some cosmic rays, etc. So there really is, how can I process the data in a certain way that kind of gets rid of some of my errors without actually encoding the information redundantly. And I just want to make a quick comment on the previous discussion, since I didn't get a chance to really talk there. I'm not a quantum algorithms expert, so maybe take what I'm about to say with a grain of salt. But as far as what I've seen, there is no provably useful use of quantum computers without error correction, right? That isn't to say that there won't be. right? I want to be clear. I'm not saying that NISQ isn't going to happen or there aren't NISQ algorithms, but in our view, if you don't have fault tolerance, there is currently not really much you can do with your quantum computer, even with error mitigation, because error mitigation does not give you the kinds of exponential scaling that fault tolerance will, right? So I really think that fault tolerance is kind of the only thing that's provably currently going to provide value. That isn't to say that NISQ won't, and fault tolerance is a higher bar, right? So if you are on the path to fault tolerance, and much like Rob said, you're obviously going to have systems. You're not just going to come out one day with a 1,000,000 qubit system that's fault tolerant, et cetera. You still have to go down the path of scaling from small to this end goal. But if your systems are really meeting your benchmarks and your milestones along fault tolerance, well, then if any NISQ algorithms come about that actually provide value, you'll be able to pick that up for free, right? So the point here isn't that you should only be doing fault tolerance, et cetera. It's that fault tolerance is what we know will work. If something else comes up, if you're on the path to fault tolerance, you'll get that too.
I think that's well said. Can I add one thing, just like an analogy, which is in classical computing, even though transistors are much sort of like higher quality, lower error rate than qubits, we still have error correction in all the systems that's been around for decades, right? So forward error correction in networks and ECC in memory and RAID and storage media and parity checks, and there's all these error correction and mitigation techniques that exist in classical computers today. And I think it's a good analogy to think that that's going to be required over the long haul in quantum computing as well.
Okay. Aparna, you wanted to comment?
Yeah, I just wanted to say, when you think about error mitigation, I want to go back to fault and fault tolerance and error mitigation and come back to the statement, right? So when you think about fault tolerance, it requires a high degree of redundancy in quantum hardware, which is really expensive and difficult to implement. That's why you're talking about like the size of the qubits. When you think about error mitigation, it can actually be achieved by using simpler hardware, but it actually requires the same computation to run several times. So it's computationally expensive. Now, as you're making the progress on the hardware and as you're improving your performance, quality, and the speed of the qubits, you can actually afford to have, this is where we are coming from, right? Where you can afford to have that overall, even if you can afford to have the expensive computation overhead and still be able to find advantages. So I think the big difference, what we are actually talking about here is, look, in 2016 or 2014, when we put the first 5-qubit machine out, people looked at our roadmap and said, you guys are crazy. You're never going to be able to achieve what you achieved. And we've actually, as a technical field, I think over the last 10 years, we moved really fast. So I would say, don't sign off and don't say error mitigation is not possible, because we are still discovering a lot of unknowns in quantum. And we do believe that's a valid path. And yes, the fault tolerance would be nice, but I probably will be dead by the time fault tolerance comes. So meanwhile, I want to really make sure that quantum is actually useful and deployable for our partners and for our clients. Otherwise, it's not meaningful.
Yeah, thank you. And one thing I wanted to add to that, and then we have a couple of questions from the Q&A I'd like to answer. Maybe for those who have joined the quantum sector relatively well recently, I must say we've seen tremendous progress in the field. I did my PhD back in 1996. At the time, we were not talking at all about quantum information science. That's not so far away. Started investing in 2018. That's just 5 years away. Also then, I mean, there were many unknown, many questions. It's amazing to see, in my perspective, the level of progress, both on the algorithms, on the hardware. Of course, there's not enough qubits. The fidelity will get better, but I think it's fair to recognize that we're on a trajectory that's pretty amazing. I think, and I don't know many other sectors where we have this kind of dynamics actually. So we have a tendency sometimes in the quantum sector to bang ourselves on the head. But I mean, progress has been very significant. I mean, testament is that, well, you guys are here and are talking about applications of quantum computers. 5 years ago, it was not possible. I mean, that's to me something that's really amazing, and we must stop sometimes and think a little bit about that. Thinking about applications of quantum computers in itself is a huge progress. Anyway, so going to the questions, because we've got quite a lot.
Sorry, no, I just like to add something about the debate FTQC versus NISQ. The point is, I mean, no client can wait 15 years to see something, and I think people should stop to oppose NISQ versus FTQC, because if we stop NISQ, then nobody is going to develop a fault-tolerant quantum computer. It's going to take way too much time. So NISQ is a must now, and people should start with NISQ, should learn quantum, should try to get as much as possible from NISQ infrastructure, and then eventually we switch to the better ones, which will be probably FTQC. But hoping that from one day to another, we are going to do fully classical, and then if FTQC comes, we are going to switch magically. I think it's a mistake. We need those different steps. Hybrid, classic, NISQ for now, then probably because NISQ is going to improve, hybrid NISQ plus a touch of FTQC, and then maybe hybrid classic FTQC. But I think that should not be a debate. They are both very useful. We need to find application. As mentioned at the beginning, we still don't know what quantum computers are good for. So let's try to find application first.
Yeah, it's kind of just quickly add on to that. Again, my point isn't that we shouldn't be doing NISQ. My point is simply that I personally have not seen any proof of NISQ providing value yet, right? So that isn't to say that people shouldn't be looking into that. I obviously would love someone to find a great NISQ algorithm, right, that really works. My only comment is that we should be sober to the fact that that isn't the case right now, right? And I think promising otherwise is very dangerous in the sense that, you know, you're over-promising and hopefully not, but you may under-deliver, right? Which can cause more damage than otherwise. So I think we just need to be true to the fact that we all want NISQ to work, right? I don't think anyone here doesn't want NISQ to work. We're all rooting for NISQ. But as far as I know, it's currently not here.
Okay, so that brings me to a question, which is in a list of questions by Svetoslav. How to separate the great promise from snake oil? Which are some easy to spot deficiencies in pitches or speeches, which would reveal a snake oil in quantum? I think that's a good one. When you're hearing about people talking about quantum, and when you see articles, Financial Times, The Economist, etc. There was a big paper in The Economist a couple of months ago. So, and precisely to your point also, Barak. So how do you make the difference actually? How can people really form a rational view on quantum technologies and quantum computing in particular?
Yeah, so I think that the thing to just accept is that quantum computing is a really, really hard problem, right? This is, however hard you think it is, it's even harder than that, and it's even harder than that, right? Every day, even today, you know, kind of the metrics that we use are even changing as a function of time, right? Because we're still not exactly sure what the best thing that we should be quoting is, right? It used to be qubit number. Okay, now there was quantum volume, then there's clots, et cetera, right? So we're still in this regime of figuring out, you know, how are we going to, you know, what do we need to build something that has practical value? And to kind of take that one step further, you know, even when you get into the detailed, the nitty-gritty details of a technical discussion, you know, you'll start with lifetime. Okay, but lifetime's, you know, kind of a meaningless number. It's actually error rates. Okay, you have error rates on your single qubit, your 2 qubit, but then you have measurement that you have to worry about, leakage, which is something that error correction can't natively typically deal with. You know, cycle time, how long is my measurement going to take? How long are my gates, et cetera, right? So there's lots of nitty-gritty detailed things that we all have to work out. And if it was obvious, you know, which one of these platforms was the one that was going to win, well, then only one of us or maybe none of us would be here, right? This is a very hard problem that we're all trying very hard to work out. And one more thing I want to add is, people often, I get asked, why superconducting, why atom, why ion, et cetera, right? And at least to me, there are obviously pros and cons to each platform, but really we all work on what we work on because it's what we worked on, right? I'm not working on neutral atoms because I just don't have the experience with neutral atoms. My experience is in superconducting qubits. So I know how to kind of push that forward, right? And that's similarly the case for people working on ions, cat codes, neutral atoms, et cetera, right? So we have a bunch of very smart people, with lots of experience in their respective fields trying to push their fields forward. And the point is that it's just not obvious which one of these is, which one, or maybe multiple, right? Which are gonna come out and hit the benchmarks that we need. So I think the thing is, anytime you see a statement that's, broad and vague, like that's the snake oil. This stuff is very, very hard, and really the fine print matters.
Yeah. And I would have a question as well. In modern physics, I think the principle for physicists, is to be really focused on their sector. When you get a PhD, a postdoc, very narrow, maybe 50 people in the world are really interested in the end in what you're doing, or really understand truly what you're up to. How can we build on that, actually? How can we build a generation of also entrepreneurs, managers for quantum companies that have maybe the ability also to see through the shortcomings of some of these technologies and be a little bit more, let's say, objective in a sense, because each company, like you guys, like Rob, Bharat, over startups as well, and Aparna in some way at IBM as well, have a clear focus to start with. How can you get the expertise, the experience to judge your technology with respect to alternatives, actually, and avoid sometimes going maybe too far into statements that are not just because you cannot know everything about every technology, as you say, Bharat, it's very, very complicated. So how do you deal with this complexity and the really difficulty to be aware of everything that's going on and to have an opinion about it, actually? That's also a question for us investors. That's we have to deal with that. We need to find a way to make a difference between these technologies and have a judgment that's as objective as possible. That's tough. And how do you do it in companies? Question also to Robert, actually. How do you judge these different technologies, and who do you pick and why?
I think, go ahead, sorry.
No, go ahead, Rob.
Okay, I was gonna say, there's probably two approaches. I'm not a physicist, right? So I bet my career, at least this stage of my career, on atom computing. And the question is why, right? And how do you sort of manage that risk? Because there is risk. I think I agree with what Roth said, is there's these different modalities because we don't know what's going to win. And there's different expertise and different ways of building these qubits. And so you've got different teams pushing forward. And so how do we manage that risk and figure out, is ours going to win or not? So we don't just depend on luck. Right. And to me, it's like identifying what needs to be built. What is the pace that needs to be built at? What are the risks? What are the technologies that don't exist that need to exist, or the ones that exist that need to get better? And just putting a plan in place and getting commitment of a team and the experts to try to experiment, fail fast, and push forward as quickly as possible so that we can make sure we're on the right track. And if we're not on the right track, that we course correct, or I don't expect long-term all of these different modalities are going to win the race. I think one or two of them will probably win the race, and people will adapt and move and consolidate over time as that takes place, but it's just too early of days. So, as a leader of a highly technical organization with 40 PhD physicists in it, it's just about put a plan in place, fail fast, and course correct, and keep your foot on the gas. And that's kind of what we do.
And I just want to add to that. At IBM, we've taken an ecosystem first approach to this. What does that actually mean? We opened our systems, we got in people to actually use the systems, and that has built ecosystem, right? In a nascent technology like quantum, I think it's also important to understand and learn from each other as much as setting the trajectory, because you are taking an approach, your ecosystem wants certain things, they give you feedback, you learn from them in the process, and you actually shift and you add more based on where others are going as well. So I think there is a little bit of collaboration which happens around, and you have multiple of stakeholders. You want to understand how do researchers actually look at quantum, but you also want to understand what are the businesses and what are the needs for startups in that ecosystem, and then take it collectively and inform how you push your agenda forward and how fast do you accelerate on certain things, and certain things you stop doing. So that's the approach we've taken as well across the board.
Mm-hmm. And Robert, how do you choose your partners?
And we try to, I mean, that's exactly what close to what Rob mentioned. You try and fail fast. So all platforms will probably have an impact on, I mean, there will be a couple of problems per platform. So we are trying to understand first what each platform can do, what are the roadmaps, are they credible or not? Because if we invest, we want to be sure that the partner is going to last for at least 5 years so that it pays off in the end. So that's a very strong filter also. And then when we identify that the partner seems robust, we try to, based on our understanding of the platform, try to find in our computational workflow what are the problems that could fit, both in terms of size and physics of the problem. So very often in the end, we end up having to rethink, redesign the problem, the algorithms, etc., to find a way to match our workflow on the platform. So there is no, so far, unfortunately, we don't have a magic recipe. We try everything and we hope it works for the best.
Okay. And so switching gear a little bit, I wanted to ask you all, so there's a specific dynamics in the economy, as we all know. There's Silicon Valley Bank, there's inflation, general macroeconomy that's going, not exactly according to the plan, I would say. Do you think this has an impact on your companies, on the technology, on the deployment of quantum technologies in the short and in the long term? Is there more interest, less interest? What's the relationship to your investors or stakeholders, shareholders sometimes for big companies? Maybe they ask you to focus a little bit more on the short term. And maybe for startups, they say, okay, the same thing, show me the short-term results and the applications that your technologies are helping to achieve. Do you see more pressure towards application in the current context or not?
I guess I can start. So I think as a startup company leader, you need to find the right investors and the right partners who have the right expectations for what is achievable, and not take money from someone if they say, oh, we want you to have $100 million ARR next year, and prove some NISC application for some use case that isn't proven yet. I think it's just unreasonable expectations, right? And so you need to find the right partners and take money from people that have the right long-term view that this is hard. It is going to take multiple generations in order to get large scale quantum computing at commercial scale. And we hope we'll find use cases along the way. There is a market. I think Aparna can attest there is a market for quantum computing today. And we want to participate in that, but we need to make sure we pick partners and investors that have reasonable expectations and are really focused on giving us the time and opportunity to scale up the technology and get the fidelities up and all the other performance metrics that are required in order to have, build a $1 trillion, industry. I think everyone acknowledges this is going to be a $1 trillion industry someday, but it's not going to be next year. It's not going to be 2 years. It's going to be something a lot further down the road. So the rewards are going to be great for those of us who get there, but we've got to have a realistic expectation of the timeline.
Okay. Anybody else wants to comment?
One thing that is important also right now is to build the IP portfolios. The one that may, be barrier to entries to other competitors. So that's also one of the reasons to try immediately quantum computing, even though the machines are probably the ones of the future, etc. It's because you want to have a strong IP position, and that's only as being one of the leader of your market that you can do it.
Yeah, Aparna,
I think Bharat was about to say something. I can add after Bharat.
Yeah, thanks. So, I mean, just to kind of, I want to tag along Rob's point about, it's all, life is generally about managing expectations, right? And I think it is important to, find investors and get investors that understand, what this technology is, right? This is a longer term technology. It is, fusion-esque in some sense. Hopefully not going to always be 30 years in the future, like was the case for fusion. But it is a long-term technology, right? And the impact, I at least, I think all of us here believe that if we build quantum computers, or when we build quantum computers, the impact will be profound, right? And there are investors out there that understand that, right? That it's when we do this, it's going to be big. And so I think the challenge is really finding those investors for startups such as Atom or Atlantic or Qubit, finding investors that understand how long this is going to take. And yes, you have a recession here every now and then, but if your investors truly believe in the technology in terms of its impact when we build it, these short-term things hopefully aren't big of a problem. Now, there are also obviously some practical things you have to deal with when the markets go down, and there's a little bit of timing there. If you raised before the markets go down, then good for you. If you need to raise when the markets are down, there's going to be some practical effects there. But in terms of the technology itself, if your technology is sound, if the milestones you've established make sense, right, and you're able to convey that they make sense, then I don't think that this is a big worry if you've constructed a set of investors that understand the lay of the land.
I think the only thing I would add to that is, as you think about patient capital, which is the investor side, right? You need investors who are patient, who understand and set expectation. On the other side, you also need people who are users who understand the expectations, right? Like oftentimes, when I get into conversation with people who are interested in quantum, earlier it used to be at the beginning when I took this job up, it used to be, hey, I have this brilliant idea of what quantum can solve. And we had to start narrowing it down to here is what we can actually do. And here's the path in some ways, and make it more realistic. Today, what we are, and I think over time, I'll give credit to this field, is over time, over the last 2 years itself, I've seen the conversation shift from I want the pie in the sky to they are actually coming back and asking, when we have our clients, they're asking for a smaller piece and they want to do proof of concept. So I think understanding, setting expectations, not only for VC, but also the users, is two sides of the equation, which is important as you're thinking about the changing market and the impact on the market.
Mm-hmm. Thank you. I heard your participants, maybe to have a look at the Q&A. There are some questions I think you can answer directly. I think some of them are directed to you. I think there's one for Bharat at least, one from Robert. I mean, we will not take them necessarily here. I would have a question about national plans in particular and government support. I think that's something we've seen a lot over the years. The UK had started with a pretty aggressive or really focused plan a couple of years ago. I think there's been some announcement from a new UK plan a couple of weeks ago. Australia, I think, is also working on something. The US has published, in France, etc. Germany. How do you see the role of governments in this sector? Is that, well, I guess there are some good things with that. There's some funding, non-dilutive funding, that's also obviously very nice and important for startups. On the other hand, we hear a lot about sovereignty issues, restrictions to export, for example, for these technologies, which could be a limitation for the market development as well. How do you perceive that? I mean, restrictions of this kind, definitely, I think that's way too early, the way for the kind of situation we're in. On the other hand, that's also to be expected. How do you, startups, IBM, large groups, deal with governments actually? And are they generally speaking, a plus for you, for your development? We're playing a good role. Could it be better? And what needs to be improved or changed eventually?
Yeah, maybe I can start. And I'd like to share a few words about how we interact. Actually, for us, it's very good since there are two things. The first one, and we have schemes in France that supports long-term R&D. So that's always interesting because at least we can take the risk. And as it was stressed by everyone today, we still don't know what to expect from quantum computing. So that's a way to mitigate the risk getting funded. The second point that is for me even more important is that we see government buying the first quantum computers and giving free access in their national supercomputing centers to these machines. And that's for us also very important because at least we know the machines will be available and all the investment that we do in developing novel codes will pay because we can have access to machines, test at large scales, etc. And we wouldn't do it if it wasn't the case. So for us, at least that's very positive to have access to these machines because we need them as soon as they are ready.
Yeah,
I think for Adam,
actually also one question I wanted, if anybody also can say a few words about this buying machines approach, which is very popular in Europe, where plans are into well, governments have sponsored direct subsidies, I'd say, through procurement to startups, which has not been so much the case in North America for now. I mean, like putting that on the table if anybody wants to talk about that as well. Rob?
Sure. Yeah, I mean, I think to answer the first question first around government interaction, for Adam, it comes in multiple forms. It's all quite positive, right? So the first form is both universities as well as national labs. We have, multiple R&D collaborations going on in different sort of subsystems within our technology, where we can advance the state of the art and get access to, collaborators and smart people who can help us advance our technology, and then we help them advance their research at the same time. So those are good mutually beneficial collaborations. Some of those then also get funded by the US government. We have multiple grants from the National Science Foundation and from DARPA to help offset some of the costs of those collaborations, which is quite helpful as well. So those are probably the two primary types of interactions that we see, strong positive effect on our business. As far as systems, I think it's very similar to like supercomputing systems, right? Certain jurisdictions, whether they're supercomputing centers or national, labs or defense or intelligence or whatever, they just want to own their own system. They want to have full access to it. They want to control what kind of research and applications they can write on top of that. They might have data sovereignty concerns or data security concerns, or they might just want that technology in their jurisdiction just so that they can have an ecosystem of innovation around it. And I think it's the same with quantum computing. And it does seem to be stronger in Europe than anywhere else. In the US so far, they seem more interested in just, getting time on the systems than buying systems. I don't know if that'll always be true, but that seems to be true for now. But, I think it's just people wanting to have, some control for whatever the reason is of a quantum platform or a hybrid HPC quantum platform inside their jurisdiction for their, for their citizen, their constituency, whether it's a national defense or research agenda. It just depends on the organization.
So I think government plays a critical role in quantum computing. Like we actually have a lot of national labs, both internationally and in US, who are part of our ecosystem. We're also engaged at different levels, and where they play a huge value is in accelerating research and development in their communities, in actually enabling the talent development and workforce development, and finally in some of the economic development, specifically with industries. And as far as the systems, I have 6 computational centers within my ecosystem where IBM has sort of it's IBM owned systems, but dedicated to these entities. We recently, on 24th of March, we announced our deal with Spain, which is with our Basque government. And what that does, this is an example which I'm using. Why did BASC actually engage with IBM to get an IBM-owned system specifically dedicated to BASC? There were reasons exactly what Rob highlighted. There is a question around, hey, we want to own the data which goes specifically around it. We want the flexibility to give access to our researchers and be able to do it in a way where we control how much access we give to them. And third, we want to really create this local innovation hub in the Southern Europe area, which is important for the government as it's growing its ecosystem there. So those are the reasons why Spain has done this. There are other governments who are more focused. As example, in Korea, we have a system where they're more focused and worried about where does data go and how do I think about data centricity, etc. And that is the primary reason why they choose to work with us in that fashion. And in Japan and others, they are actually looking at how does the HPC, I need to think about latency. I need to put it next to systems where there are HPCs. So I think the answer differs slightly depending on what the government actually wants and what is primary for them as you're thinking about it, but it touches the areas which Rob has spoken about previously.
Okay, thank you, Aparna. Now I will ask one last question that came up into the chat as well, and I think it's a big question, big concern, and focus of discussions between Robert and me actually these last months. So the question is, how do we scale up to $1 trillion market estimates from where we are? It has 26 computers, IBM, ones of prototypes. When do you see the tipping point where QC sales really take off? And that's important topic. I think something I'm a little bit, that troubles me a little bit. Let's imagine within 2-3 years, we have some applications, quantum advantage for NISQ era machines without error correction, but maybe with error mitigations, as we said before. How do we build the machines actually? How do we address the customer's needs? Because all of a sudden, there's more of a market. It's hard to build machines like Atom's machines or Atlantic's machine. It takes time. It's not overnight. It's not a semiconductor business. I mean, then there is construction, orders, etc. How do you see the dynamics there? What happens between quantum advantage and really the market taking off for you actors in the quantum computing market, both on the hardware side and also for Robert? How do you bring these innovations at scale really for your end users? Maybe let's start with Robert, maybe.
Yeah, I can start because it's probably the easiest for me. We are the end user. I mean, we use the algorithms to improve our own computational platform, and we sell the outcome of the use of our platform. So, of course, we hope that we'll have access to more machines, even imperfect, even with limited number of qubits. But today, the biggest hurdle is more than the limitation of the machine itself, is limitation of the access of these machines. It's very hard for a client to get access to any machine at all. So we hope that based on what everyone discloses, public information, that it will be more available in the next 3 to 5 years. That's why we took a road towards emulating quantum qubits on GPUs, because at least we can do the computation that we want without waiting. But it's it's tough. And clearly, even short term is quite long. It's 3 to 5 years when we speak about having access to such types of machines.
Okay, Rob?
And government will play a key role, as we mentioned before.
Yeah. How will you build all these machines once quantum advantage is on the horizon? Let's say.
How will we build them? I mean, I think I very much look forward to the day where we have designs that are, correct enough and have enough, fidelity and performance and so forth, that we're in an enviable position where we can just build copies of them and satisfy the demand. I think that we kind of look at it from the end state and then back up. Like, what are the algorithms or use cases that could have tremendous economic value? right? And we've talked about some of them here in transportation, logistics, pharma, chemistry, banking, et cetera. And there's no doubt that if you can just eke out, small fractions of efficiency percentages out of any of these industries, you can create a very large monetary value. And then you have to ask yourself, well, how many logical qubits are required in order to, satisfy some of these use cases or algorithms, and try to estimate that. And then how many physical qubits with the error correction schemes and the error rates and all that you're projecting would be required. And then how are you going to build a system of that scale? So that's kind of how we do it, is look at the end state and then try to back up and figure out what's required and how are we going to get there and how are we going to fund it. And I think the way I look at the market, and I could be wrong, I kind of feel like there's going to be a couple of eras. There's going to be the era we're in now, which is, people call it the NISQ era, but I think about it as these systems are desirable. There's a lot of demand for them. But the demand is really to experiment, do economic development, workforce development, understand how to program these systems, get some results, things like that. And I think that market will be orders of magnitude smaller than the future era, where there's economic value, commercial value at scale for some of these other use cases. And I think that's when it gets unlocked. And so I don't know if that's 3 years or 5 years or 7 years down the road, but I think it's somewhere in that range is when we'll transition out of the kind of current NISQ experimentation era and a smaller market into a much larger commercial value at scale market.
Okay. And Aparna and Bharat, maybe last words before we close the session.
From our perspective, we've actually very publicly put out our roadmap. So we work towards that. When we are building our systems, and we have 26, it's not just about getting the systems out. We are actually putting the systems which are available almost all the time to our ecosystem. So as we are building this, we are actually in the labs, we have our next generation, we are testing on performance. We are testing on, does it meet the minimum viable things which we want before we put a product out. So I think as we grow, we will continue on this journey of actually announcing the direction which we are doing and track it with that. Bharat?
Thank you.
Yeah, so maybe I'll just
last word to you, Bharat.
I'll just add a little bit onto what Rob mentioned. Like currently the use cases for quantum is education in terms of getting people acquainted with what is a quantum computer, workforce development, as he mentioned, and so that is a very small market, right? And it's going to be a big change once people realize that they can actually do something with these machines that either allowed them to do something that they couldn't do before, or allows them to do what they could do today, but much cheaper, right? So those are the two things that need to happen for this $1 trillion market to really open up. And there needs to be a whole supply chain that has to be established for that, right? Again, we're still in this early development cycle where, the things that we use today, the supporting infrastructure, et cetera, may not be what we actually need and use in the future. So I think, in addition to the chips themselves, we often focus a lot on just the quantum chips and their performance, et cetera. There's a significant amount of overhead that needs to be, we need to build all the infrastructure that supports these systems. And I honestly don't see any shortcut to this. I think it will take time. But as the use cases start to become more and more clear that they provide real value, so will the money, and hopefully that helps accelerate those issues as well.
And Christopher, I know that you said Bharat has the last word, but I would just say that I think our timelines in our minds are slightly different, right? I'm saying, hey, over the next 5 years, we should be able to see some of these unlocks, which will happen as we go. And yes, there may be a provable path with error mitigation. And I think the proof is yet to come. I agree with that. The proof is in the pudding. But I think the timelines wise, there might be a discussion around, is it nearer or is it much further away? And if it's 30 years, then I don't know if there is patience in the market for a 30-year life cycle to wait for it. I think it has to be progressive timelines.
Thank you. Thank you all.
Thank you all for this awesome discussion. And on that note, thanks to IBM, Google, and venture funds like yours, Christoph, for funding this, and the various governments for funding this endeavor. We appreciate and are grateful to all the panelists today, and especially you, Christoph, for moderating this. And hope to do other quantum events with you. Thank you all, and thanks to the audience for staying here. Olivia?
Yeah, thank you everyone so much for joining. Thank you, Christoph, for moderating, and all of our panelists for joining the events. The recording will be available later, probably tomorrow, on our YouTube channel, so feel free to watch that just to catch up on the event. But yeah, aside from that, thank you so much, everyone, and have a wonderful day and evening.
Thank you all.
Thank you all.